Hi there and welcome to this video for Senior Physics on electrostatics and electricity. In this video we're going to explore resistors in a series and parallel circuit. Now let's just recap. A series circuit basically is a circuit which has one continuous loop, which means that the resistors go side by side and the current flows through them. Now if you've watched the previous practical videos which were earlier on in this course, you will have seen the effect of what happens when we place two light bulbs together in a series loop. And the result is that we get, if the more light bulbs we add in a loop, we decrease the amount of voltage. Now there are a variety of laws that we need to apply, and then we can apply and work out the total resistance which is occurring within the circuit. So you can see here that we've got a circuit here which has got two resistors, R1 and R2, and they're linked to three batteries which have a certain amount of voltage which we'll call V. We see that we've got a current, A, which has been measured with an ammeter, and we've got it on both sides. We also can measure the voltage V1 and V2 across each of our resistors and see what we get. Now what we find is that current is measured by the ammeter and it has the same value through each part of the circuit. What this means is wherever we place the ammeter, the current is always going to be the same. Watch the practical video and this will demonstrate that. We also notice that the voltages V1 and V2 will add up to the voltage which is gathered by V from the battery. Now, I work on the idea that the voltage is the delivery system. That is the amount of energy. That energy has to be shared between those resistors. If the resistors happen to be the same type of resistor, then the same amount of energy is given to each one. So we just divide the voltage V by 2 in this case, or 3 if we had further resistors. The result is they would get an equal share. However, if you've got a resistor which is going to be give up more resistance, then the result is it's going to give out more energy. So it will take the lion's share of the total amount of energy V. But the key thing to understand that the voltage supply, or Vs, given by the battery will be shared between V1 and V2, or shared between R1 and R2, giving out the energy V1 and V2. As a result, if we then put this into our system, we basically know that the current is going to be the same all the time. So we can get an overall series resistor or series resistance by combining all the resistors together. And we do this using the algorithm that the resistance in a series circuit can equal R1 plus R2. Now the way of thinking of it is R1 and R2 gives a resistance to the overall loop in the circuit. So it's like having one big resistor in there. This just happens to be made up of two components. But what we are trying to do by using this algorithm is work out, well, if I was going to take these two components, put them into one big resistor, what size would that resistor be? That resistor then controls the flow of the current throughout the circuit. And remember that the voltage across that resistor must equal the voltage coming out from the battery. So that's how a resistor works in series. So let's have a look at what happens in parallel. So now I've got the same circuit, but in this case I've got R2 and R3, and they are placed in parallel. I've got an ammeter, A1, coming from the battery. Then I've got two currents, A2 and A3, going through each branch. So I'm measuring with A2 and A3 the current I2 and I3 going through the branch as it flows into it from I1. And what do we notice? Well, the currents in this case basically split up. Now they don't split up in twos. They will only split up in two because I've got two branches if the two resistors are the same. Now the key thing to understand is that charge will take the path of least resistance. So you'll get more current flowing through a resistor which gives up less resistance to it. You can basically work on the principle that it can get through easier, so more is likely to be pushed through. With a higher resistor, the result is there's a backlog of charge, which means it's slower to get through. As a result, the current will be smaller. Now what we find is that the two currents going through each branch will add together to equal the total amount of current coming out of the battery. Now, as I said, if the resistors are the same, then the current will split in two. If R2 happens to be twice as big as R1, then we'll get half amount of the current going through it than it would normally have compared to R3. So I hope that makes sense. Another way to think about it is think of the A1 being like the freeway or the highway. And basically you've got, let's say, 5 lanes of traffic coming out at A1. Now when you get to A2, let's say A2 happens to have 2 lanes going off. What we will then get is 2 lanes of traffic will be flowing off. And if I was to count the current, the amount of cars, I would only get a certain number of cars coming off. However, R3 will have 3 lanes of traffic coming off, which means I'm going to get a third more current going through R3 than I will have through R2. So the result is that the current flowing through R3 will be bigger than the current flowing through R2 because it's got more lanes. The result is that R2 and R3, the current going through R2 and going through R3 will equal the current going through I1, okay, because basically they're all coming from the same point. So we're looking for the path of least resistance is where all the current will go. So as a result, we get an algorithm that I1, the current coming out from the battery, will equal the current in I2 and the current in I3. This is really important for you to progress, and you must learn this. Also, we need to know that the voltage is the same across all branches in parallel. So what this means is that if I was to measure the voltage across R2 and R3, they would equal the voltage coming out of the battery. Now, why is this? Well, let's go back to my car scenario. Basically, each car, if we say the car is a charge, each car will carry the same amount of energy. So as it passes through each of the resistors, it doesn't matter what car I'm looking at, each car will have the same amount of energy which it can deliver to that resistor. The only difference is the number of cars which are passing per second. They're still giving up the same amount of energy. So if you think of the car going per second or being counted per second as the current, and the actual size of the cars or the amount of energy is what's carried inside, each car carries exactly the same energy. So it gives out exactly the same amount of energy. Okay, if we've got 2 resistors in that one parallel branch, then that energy will be split between the 2 of them. 3, it will be split between the 3 of them, but there will still be the same amount of energy as was picked up from the voltage from the battery. So the voltage in a branch in a parallel circuit will remain the same. So from this, what do we get? Well, the total resistance for a parallel circuit uses the reciprocal rule, which basically means 1 over R, the resistor in parallel, will equal 1 over R2 plus 1 over R3. So what we're trying to do here is to work out, if I combine those 2 resistors together into one, what will I get? So the key thing to understand is this is in the form of a fraction. So it's very easy to make the fraction and work out the right-hand side and convert it into one fraction. The key thing to understand is you then have to inverse that final fraction to find out what RP, or the total resistance in parallel, is. Okay, well the best way to work on this is to actually work through an example. So here I've got example 1, and we're going to work out the total resistance, RT, for a series circuit. So I've got a battery, I've got R1, I've got R2, and I've got R3. R1 is 10 ohms, R2 is 20 ohms, and R3 is 15 ohms. So in order to calculate this, we know we need to go back to what we learned in the previous slide, that basically we add our resistors together. So we get RT will equal R1 plus R2 plus R3. So I'm combining those 3 resistors to make one overall resistor. The effect of that is that it will produce a single current. So from this I get RT will equal 10 plus 20 plus 15. So I get that RT equals 45 ohms. Simple. So, how do we work on a parallel circuit? Well, let's look at this example. In this case, we want to work out the total resistance RT for a parallel circuit. So I've got the same resistors, but now they are in parallel. So we have to use the reciprocal rule. So the reciprocal rule basically states that 1 over RT equals 1 over R1 plus 1 over R2 plus 1 over R3. So I get 1 over RT equals 1 over 10 plus 1 over 20 plus 1 over 15. If I combine together the right-hand side into one fraction, I get 1 over RT equals 13 over 60. Now that's it simply done on your calculator. But the key thing is there, the answer is not 60. And this is a problem that I've noticed with a lot of students. They forget that it's 1 over RT that equals 13 over 60. So what I've got to do is inverse the fraction. So as a result, RT will equal 60 over 13. So you can do this just by hitting the x to the negative 1 button, your inverse button on your calculator, or you can do the algorithm very, very simply. As a result, RT will equal 4.6 ohms. Now, what I've got for you is a series of exemplary videos which will help you work through this. So I hope you find that useful, and I look forward to you joining me again. Bye for now.